All right, friends, welcome back. As I mentioned in my email to you, we are maybe a half a lecture to a lecture behind. That's okay. That's okay. We're moving, not behind anybody, not behind the 10 o'clock class. They're actually even behinder than you, so yay. But that's all right. I built some flexibility into the schedule later on, and as we get closer to the exam, if we're not ready for everything, I'll edit the exam accordingly. So no worries. We'll finish chapter 13 today and probably move on to chapter 14 towards the end. I'll keep you posted with emails to help you know what schedule to be on. Now, we were talking about using reducing agents like lithium aluminum hydride with aldehydes and ketones, which was pretty simple. Re-recording, yep. But we're not, but you can't see it. Oh, okay, that wasn't your question. All right. Better? All right, thank you. Dang. So, yeah, talking about using reducing agents, it's pretty straightforward with aldehydes and ketones. There's no good leaving group on the tetrahedral intermediate, so you get a nucleophilic addition product. With acid chlorides and esters, other things with leaving groups on the carbonyl carbon, it gets a little trickier. The problem with lithium aluminum hydride as your reagent is, yes, you deliver a hydride to the carbonyl carbon and get this tetrahedral intermediate, and yes, there's a good leaving group relative to an oxygen, so you get the aldehyde, which is nucleophilic acyl substitution, but the aldehyde is itself about as reactive as the acid chloride, and so it will go on and react with another molecule of lithium aluminum hydride in a nucleophilic addition reaction to give you, in the end, the primary alcohol. So the idea is with lithium aluminum hydride, you can't stop at the aldehyde. So in effect, anytime you're reacting lithium aluminum hydride with acid chlorides or esters or anhydrides or other things with a good leaving group, that's an eraser, not a pointer. There we go. You're going to assume we've added enough lithium aluminum hydride to equivalence to go all the way to the alcohol. Okay? Now, organic chemists like options. So one problem to solve is, could we possibly stop at the aldehyde? What if I don't want to make the alcohol? And the answer is yes. There's a couple of different reagents that do this. Unfortunately, your text doesn't describe why they work. Dibol works for a reason that's pretty easy to understand, but that we simply don't have time for. It's not in your text, so we're going to skip. That means you got to memorize that dibol stops at the aldehyde. Okay? Sorry about that. I don't like memorizing when we don't have to, but if you want to know more, come talk to me. It's a pretty easy explanation, maybe 3 minutes, and you can see how it works. Your text says, well, it's just less reactive than lithium aluminum hydride, and I suppose that's technically true, but there's a little bit more nuance to it. It's kind of a fun explanation, but we won't say more about it. A second reagent, and again, why are we doing two instead of just one? Simply because organic chemists like to have options. This is lithium tris-tert-butoxy aluminum hydride. Unpronounceable and almost unwritable. The electronegative oxygens, it's thought, perhaps decrease the amount of electron density on the hydride, making it less reactive. So as with dibol, this lithium reagent with the tert-butyl groups can stop at the aldehyde. That's going to be something you got to memorize. Now, when you need to memorize a reagent, remember what it does. You can do whatever works well for you to memorize. I find it perhaps useful to think about a reaction in 3 different ways. So let's just use dibol because it's easiest to write. You could imagine making flashcards for yourself that involve an acid chloride or an ester, and then you write dibol at the top, dibol hydride, and then you have to fill in what the product would be. You could imagine an alternative flashcard where you have the ester starting material and the aldehyde product, and you have to remember what the reagent is. In this case, it could have been either of these two, either dibol or the let's see, it's actually diol hydride, and then, or this lithium reagent with the tert butyl groups. Finally, you could imagine a set of flashcards where you write the aldehyde and the reagent, diol hydride, but then you think backwards to the starting material. Whatever works for you to memorize stuff, but that's a strategy that I think is helpful for a lot of reactions. And if you struggle to remember reagents, there you go. All right, one last thing on reducing reactions, and this is a problem from your either the study guide or the problem set, can't remember which, but I think you had something kind of like this. And the idea was that lithium aluminum hydride is too reactive to be selective. So you have this starting material and it has a ketone and it has an ester. Now what you should remember from the first few times that we've talked in class is that ketones are more electrophilic than esters because ketones lack a good electron donating group, which is what the oxygen is on the ester. We've also talked about how lithium aluminum hydride is very reactive, meaning very nucleophilic. So this is, lithium aluminum hydride is going to be nucleophilic enough that it can react both, and we've seen this before, with the ketone and with the aldehyde. So you would not expect, as a chemist, to use lithium aluminum hydride on this molecule and hope to reduce just the ketone and not the ester, or alternatively, just the ester and not the ketone. That kind of ability to reduce one thing versus the other we will call selectivity, and you don't expect to see any selectivity there for lithium aluminum hydride. And in fact, you would anticipate reducing both the ketone to the secondary alcohol and the ester to the primary alcohol. And I'll just draw in the hydrides that get delivered, okay? All right, however, what if we used a less reactive reducing reagent? What if we used sodium borohydride, which we've said because of the electronegativity difference between boron and hydrogen not being as great as that being between aluminum and hydrogen, sodium borohydride is less nucleophilic. This reagent can be selective. It can reduce the ketone in the presence of the ester. Why does that work? Well, because the ketone's more electrophilic than the ester. Sodium borohydride isn't quite nucleophilic enough to attack the ester, but it's good to go on the ketone because the ketone's more electrophilic than the ester. So you could expect to make the secondary alcohol out of the ketone all while keeping the ester unmodified. All right. That has an explanation, but that's another detail you may need to memorize. It works if you understand the difference in reactivity or electrophilicity between ketone and ester. It also works if you understand that sodium borohydride is less nucleophilic than lithium aluminum hydride. Yes?
Would we expect if we put like two equivalents of the borohydride, is it possible that it can do both, or is it just it can't?
It's a good question, and people probably, I don't know what the chemical literature says on this, people have probably tried it, and even if you added more sodium borohydride, it doesn't reduce the ester. Yeah. Good. All right. So that concludes our hydrogen-based nucleophiles in chapter 13. What we're going to talk about next are basically what I'm going to call carbanion delivery reagents. Just like H-, if you want to use some kind of alkyl group, a negatively charged alkyl group as a nucleophile, you need something to get it where it needs to be. The reason that we can't just use a negatively charged alkyl group on its own is, of course, because the pKa of a carbon-hydrogen bond on an sp3 hybridized carbon is around 50. So just the carbanion on its own is highly unstable. That's what that tells you. So these carbanion delivery agents involve metals which stabilize the negative charge on the carbon. And so we're going to call these organometallic reagents. Okay? And there are going to be three kinds that you'll encounter, though really only three different reagents, but really only two kinds of reagents. Two of them are going to be basically interchangeable. Why do we show you multiple reagents that are interchangeable? Well, we have to teach you what organic chemists actually do, and organic chemists like to have options. And so here are a few of the reagents. Some of them are called organolithium reagents. And the way you make these is starting not from the alkane, but from, say, the alkyl halide. So you can start with this ethyl bromide and you add a lithium metal. The little superscripted 0 there indicates that this is lithium metal. A reaction takes place, which we won't worry about the mechanism. It involves transfer of electrons from lithium metal into the antibonding orbital of the bromine, of the carbon-bromine bond. Ultimately, the carbon-bromine bond breaks and is replaced with a new bond between carbon and lithium. This reaction is called halogen metal exchange. And again, we won't worry about the mechanism for the reaction. Your text, though, because it wants you to develop skills to do synthesis, a ton of times when you need to use an organolithium reagent, it's going to make you start from the alkyl halide. Most of the time in the lab, we don't do that. We just buy the organolithium reagent, but that's how they make it. Now, you've not seen a covalent bond between carbon and lithium before. So I just want to say that that bond is a covalent bond, but it is okay to think about this reagent as though it were just the carbanion and the counter ion. That's not what it is, and actually even what I've shown you here is kind of an oversimplification based on data of what these compounds are actually like in solution, but it's good enough. You can think of the organolithium reagent as a carrier of the corresponding carbanion, all right? And you can show this reacting with carbonyl compounds in much the same way as we did with the hydrides. For example, let's use an aldehyde as our starting material. Here's an organolithium reagent. We're going to imagine that this is mostly like a negatively charged carbon with a lithium counter ion. So we'll show the bond between carbon and lithium breaking and the carbon with its electrons attacking the pi star of the carbonyl compound. The carbon-oxygen pi bond will break. That gives you your tetrahedral intermediate. And then we'll do what we've done before. This was your nucleophile that did the attacking. Here is the kicker-offer group. And there is the Y group, which is not a good leaving group. So there you are stuck until aqueous workup, where upon we get a proton on the negatively charged oxygen from water, and that gives us this alcohol. Now, you don't need to memorize that organolithiums react with aldehydes to give secondary alcohols, because if you understand the mechanism, you can think your way through, is there a good leaving group or not? You can predict the product 100% of the time, no problem. Okay? Similarly, we will see that organolithium reagents needed a little bit more space. Let's just slide that up. Will react with acid chlorides or anhydrides or esters, anything with a decent leaving group relative to a negatively charged oxygen. in much the same way that lithium aluminum hydride did. You're going to see we're going to have an exactly similar problem. The carbon attacks, the carbon of the organolithium reagent attacks the pi star of the carbonyl compound, breaking the carbon-oxygen pi bond to give us a tetrahedral intermediate with a negatively charged oxygen. At that stage, we ask ourselves, is there a good leaving group for the kicker offer to kick off? The answer here is yes. Relative to a negatively charged oxygen, it should be okay for the negatively charged methoxy group to leave. So you make this ketone, but it's not the product, it's an intermediate. And the reason it's an intermediate is that ketones are more reactive than esters. And so you've got the exact same problem that we had with lithium aluminum hydride. That is that the organolithium reagent will not stop but will attack again the pi star of the ketone, breaking the carbon-oxygen pi bond. Oops. That will generate this tetrahedral intermediate, only now we don't have a good leaving group. Here's the first, in purple, here's the first nucleophile that got added. Here is the second. Relative to that negatively charged oxygen, we don't have a good leaving group, so we're stuck until aqueous workup, where upon the negatively charged oxygen we'll pick up a proton from water, and that will give us this tertiary alcohol as the product, and we can't stop at the ketone. One of the things that's going to be useful to you this semester when we learn a new reaction is to sort of in your mind have a structural description of the product in a way that's somewhat general, and then link that in your mind to the starting material. So for example, what I just showed you is that you can make tertiary alcohols where two of the three things on the carbon are the same from an ester or an acid chloride and an organolithium reagent. So that's a structural pattern to be looking at in the synthesis problem in the text. If it says, hey, make this tertiary alcohol, and you notice that two of the three groups are the same, there's a really easy way to do that. You do that with an ester or an acid chloride and the organolithium reagent. Okay, questions about that? All right. So let's introduce the the other reagent that you can use interchangeably with an organolithium reagent. This is called a Grignard reagent. There are some practical reasons that you'd want to use one or the other. Their moisture and air sensitivities are different. They cost different amounts of money. If you take the 353 organic lab, you will do a Grignard reaction. You'll make a Grignard reagent. They are pink, which is kind of fun. It's fun when there's a color change in an organic reaction. The Grignard reagent you make from an alkyl halide starting material. And again, you use a metal, only this time it's magnesium metal. So again, the superscripted 0 tells you that the metal is in its 0 oxidation state. The mechanism is again halogen metal exchange. It involves electron transfer to the antibonding orbital with carbon and between carbon and bromine. We're not going to draw it or talk about it in any way, but after the fact, you get this molecule, which you can draw to be perfectly clear, should probably be drawn like this, but most of the time it will be drawn with just the Mg and the Br together. It is okay, even though the bonds are covalent, it is okay to think of this reagent as the carbanion a magnesium 2 plus ion, and then a Br minus ion. So you can see how everything balances out that way. Again, that's not the way it is, that's not what it is, but you can think of it that way, and that'll be useful enough. You can react Grignard reagents with aldehydes and ketones in the same way that we did above with the organolithium reagent. I won't draw, well, I'll draw the first step of the mechanism just so you can see how it's done. You take the electrons from the carbon-magnesium bond, and you have the carbon-magnesium bond break, and then those electrons attack the pi star. You would get this tetrahedral intermediate. I'll just draw for you the secondary alcohol product that you get. In the same way, you could take an acid chloride or an ester or an anhydride or anything with a good leaving group. And after the reaction and aqueous workup, you would get the tertiary alcohol, in which 2 of the 3 groups are identical. Okay? Questions? Yeah?
So that's 100% interchangeable with the lithium?
Yes. Interchangeable with the organolithium reagent, yeah.
Do you have to use bromine as the halogen?
Do you have to use bromine as the halogen? No, chlorine's quite common. Others? Okay. Well, one other thing about all of these organolithium reagents is they are moisture sensitive. So you have to use non-protic or aprotic solvents. I'm not big on showing what the solvent is for a reaction. That's a detail you get in the lab and you'll get when you take 353. You'll see it in the text a lot. It would be a disaster, for example, to use an organolithium reagent with, say, methanol as the solvent, because what would happen is before the organolithium reagent would even attack any pi star of a carbonyl compound, it's simply going to deprotonate the solvent. So instead, you need a solvent that is aprotic, but you want it to be polar, of course, because if you look at the mechanism of the reaction, you've got charges, and you've got lithium that's eventually, the byproducts of the reaction are lithium ion or magnesium ion and Br minus. So you need a polar solvent, but one that doesn't have acidic protons. Classic examples of polar non-protic solvents are ethers. So here are a few. This is diethyl ether, and this is tetrahydrofuran, or THF, diethyl ether. These are both solvents that you will encounter in the text. So learn to see them, say, oh gee, that's the solvent for this reaction, and then ignore it. Okay? Other thing is that these reagents tend to be reactive enough that we use low temperatures, and so you may see that specified sometimes in various reactions involving these reagents. All right. So with that, I need to introduce you to the third kind of organometallic reagent, and this one is the weird one. All right, so organolithiums and Grignard reagents are basically interchangeable. The weird one is called the cuprate. So I'll show you how this is made. You actually start with the alkyl halide. You add lithium to make the organolithium reagent. And then you add copper iodide, which is a source of copper in its +1 oxidation state. And then I- is the counter ion. You actually need 2 equivalents of the organolithium with the copper. When you do, you get an organometallic complex, which involves two carbon-carbon bonds with copper. If you're following along, the copper, if it's bonded to two carbons, should have a negative charge, and then the lithium is the counter ion. Where does the iodide and the other lithium end up? Well, just as a lithium iodide salt, which we will ignore. So this is the cuprate reagent. We'll have some more to say in chapter 28 about this cuprate reagent. As I said, it's an organometallic complex, and these can do very interesting chemistry involving electrons, including d orbital electrons on the metal. We're not going to talk about any of that at this point. You can, for now, it is okay. It's not, well, it is okay to think about this reagent as one negatively charged, well, that's too many carbons, isn't it? One negatively charged carbon group, and then a neutral copper-carbon complex. Some of you are going to look at that and you're going to say, why doesn't that reagent deliver two molecules of carbon instead of just of the negatively charged carbon instead of just one? The answer to that, completely, I'd have to tell you some stuff. I actually don't know the answer to that, but if I imagine it will have to do with some of the details about the organometallic complex. So, for now, you're going to need to memorize that the cuprate reagent can deliver one and only one of its two carbon groups as a nucleophile. And because of that, we're going to just make it so that they're both identical. Somebody's probably worried about, well, what if one's different? What if one's an ethyl group and one's a methyl group? Which one does the attacking? And I don't know. So instead of worrying about that, we just make cuprate reagents that have two of the same R group on them. Okay. So why are we talking about this? Well, cuprates can do things that the organometallic reagents can't. And so unique reactivity number one is cuprates can stop at the ketone. The only example of this in your text is with an acid chloride. So here is an acid chloride, and then let's use a boring cuprate reagent, the one we made above. Let's have this be the diethyl cuprate. And you can draw this mechanism as follows. One of the alkyl groups, doesn't matter which one, will leave from the copper and be delivered to the carbonyl carbon to give you a tetrahedral intermediate. Here's the negatively charged kicker-offer. Here's the potential leaving group, and here's the nucleophile that was just delivered. Electrons on the carbonyl oxygen kick down, and the leaving group leaves. The unique thing about the cuprate is we're going to stop here. The cuprate won't react with the ketone. That's unique and weird because ketones are very reactive. Your text does not have an explanation for why the cuprate doesn't react with the ketone, and neither do I. But it works. So that's an important and unique reactivity that allows you to do something you could not do with the organometallic reagent. If we're thinking about recognizing structural patterns, then one of the structural patterns here in this product is that it is a ketone, but not just any ketone. We're going to call it an asymmetric ketone. Why? Because the two R groups on either side of the carbonyl carbon aren't the same. So when you're doing a synthesis problem and it says, hey, make this ketone, and you look at it and the two R groups are different, One strategy you can use to do that very easily is to use a cuprate with an acid chloride. Yes?
Couldn't it make a symmetric one just as easily?
Sure, you can make a symmetric one if you happen to choose the acid chloride so that it's the same as the thing you deliver by the cuprate. But the point is it doesn't have to be. Okay? And notice how this is different. Had we used the organolithium reagent with the acid, or the Grignard with the acid chloride, we would have gotten the tertiary alcohol. So that's reagent-based control of product identity, and that's kind of cool. Organic chemists like to have that kind of option. All right. Second thing that cuprates do weird. Go ahead.
So if you started with a ketone and tried to react it with a cuprate, would that reaction move forward?
If you started with a ketone and tried to react with a cuprate, no, because that's why the cuprate can stop with the ketone. Okay, good. Second thing, go ahead, yeah.
So if you wanted to put two different groups on it, you could start with the halogen with the ketone, use a cuprate, and then for that product there, you could use like a Grignard.
Right, so if I wanted to make, good point, if I wanted to make, here's a good synthesis problem. Suppose I wanted to make a tertiary alcohol in which the three things were not the same. How could I do that? And the idea is, well, what if I first thought backwards and I said, okay, let's have an organolithium reagent react with this ketone. That would work. Why? Because when you get to the tetrahedral intermediate after the organolithium attacks the ketone, there's no leaving group. Okay? Where would I get this asymmetric ketone from? Well, I could think backwards and go, okay, I can get that from the acid chloride and the cuprate. Yep. Good. Okay. There's one more thing cuprates can do, and it's weird, and it will stress you out a little bit, and you mostly don't want to know about it. But we got to do it, and there's even something worse after that we got to do today. So take your medicine. All right. Second unique reactivity is that cuprates do what we're going to call conjugate addition with something else that we're going to call an alpha-beta unsaturated carbonyl compound. So first I'm going to explain what an alpha-beta unsaturated carbonyl compound is, then we're going to tell you what conjugate addition is. Here is an alpha-beta unsaturated carbonyl compound. So it's a ketone or any other carbonyl compound. Here's the carbonyl carbon, here's the alpha carbon, here's the beta carbon. Alpha-beta unsaturated means there's a pi bond between the alpha and the beta carbons. Notice that because the pi bond between alpha and beta carbons is adjacent to the carbon-oxygen pi bond, this molecule is what you learned in 351 is called conjugated. There's a conjugated pi system. They are in resonance with each other. We could use resonance to draw the following structure. This one will be familiar to you. This is the one where we move the electrons from the carbon-oxygen pi bond out onto the oxygen, and we leave a positive charge on the carbonyl carbon. We use that at the beginning of the class to tell you that the carbonyl carbon was electron poor, and that's where nucleophiles were going to attack, right? Another way of saying that with molecular orbital theory is that a lot of the pi star is on the carbonyl carbon. You guys are all okay with that, I hope. But because of the conjugation with that pi bond on the alpha and beta carbons, we can actually draw this resonance structure in which that pi bond moves over to form a new pi bond between alpha and beta, the alpha carbon and carbonyl carbons, and we put a positive charge on the beta carbon. This resonance structure tells you an important observation that alpha-beta unsaturated carbonyl compounds are electron poor Another way of saying that is electrophilic at two places. One is the carbonyl carbon, which I'll indicate there, and then the other is the beta carbon. Two places. Now, if you want to know more about this, I can show you a molecular orbital, an image of what the LUMO is for this molecule. We won't do that here. It won't help us today. We got other things we need to do. But you would see that the LUMO is also on the beta carbon. So when a nucleophile sees an alpha beta unsaturated carbonyl compound, it has to decide, will I attack the carbonyl carbon or will I attack the beta carbon? And that's important because you can see you get different products depending on which ones happen. So let me show you how organolithiums or Grignards react with alpha beta unsaturated carbonyl compounds. They're going to attack at the carbonyl carbon. So, and that's the conventional expected product. So here's the organolithium reagent. We attack at the carbonyl carbon. We attack the pi star at the carbonyl carbon. We get a tetrahedral intermediate that looks like this with a negatively charged oxygen. And there we stay until, because there's no good leaving group, until aqueous workup. And then the product is this, an alcohol here, and an R group here. The two things that got added are the R group from the organolithium reagent and the hydrogen from water, and we call that a 1,2 addition product. Okay, that's sort of conventional attack. What's new here is that cuprates attack alpha beta unsaturated carbonyl compounds at the beta carbon. Your text doesn't explain why. There is an explanation why. It's somewhat complicated, and really, even if you were a chemistry major, we wouldn't say a lot about it until maybe your senior year. So I think probably we'll just leave this as a memorized detail. If you want to know more about why cuprates prefer the beta carbon, you can come talk to me. I don't actually understand it that well myself, so I'll just give you my hand-wavy explanation and then we'll move on with our lives. But there is an explanation, it's just your text doesn't talk about it. They want you to know the reactivity though, because again, reagent-based control of outcome of the reaction is kind of cool. If you can start with the same starting material, use a different reagent and get a different product, that's pretty interesting. So, how do you show cuprates attacking at the beta carbon? A couple of different options here. It helps to keep in the back of your mind this resonance structure that I drew above, where the beta carbon is positively charged. In fact, if you want, you can draw the mechanism from that resonance structure. The way you would do this is electrons from the carbon-copper bond will attack the beta carbon, and then electrons from the bond between beta carbon and alpha carbon, that bond has to break or else we'd have too many bonds to carbon. And so we'll simply move those electrons out onto the alpha carbon. So here in red is the new bond we made with the beta carbon. Here is the alpha carbon that's negatively charged. Okay, and this is an intermediate. It's resonance stabilized, so I'm going to draw the resonance structure for this intermediate. Again, here's the new bond that we made. You can actually, because the negatively charged alpha carbon is adjacent to the carbonyl, you can move those electrons over to form a pi bond between carbonyl carbon and alpha carbon, like this, and then move the pi bond between carbonyl carbon and oxygen out onto the carbonyl oxygen. So this is the resonance structure of what I drew above. Remember, resonance structures don't mean electrons are hopping back and forth. They just mean that the electrons that are on the alpha carbon are actually delocalized onto the carbonyl oxygen as well. This intermediate is called an enolate, and you will see enolates a ton of times in 352. This is maybe the first time you've seen one, but you'll see them a ton of times in 352. Now, what happens next? What I'm going to show you is more detail than you want to know, but you're going to need to understand it to know why we call this attack at the beta carbon a 1,4 addition reaction. So start with the idea that the negative charge is both on the alpha carbon and on the carbonyl oxygen. With that in mind, when I do aqueous workup, you can imagine protonating at two different places, right? You could imagine protonating on the carbonyl oxygen. That would look like this. And that's going to give you this product. Here's the R group that we added. Here's the hydrogen that got added. Carbonyl, carbon, alpha carbon, beta carbon. That's the new bond to the R group that we got. Alternatively, if you protonate on the alpha carbon, you get this product, almost exactly the same. Carbonyl carbon, alpha carbon, beta carbon, only the proton gets added to the alpha carbon. There is a relationship between these two products. They are called tautomers because they differ only in the location of a pi bond and a proton. You can see the things that are different. Pi bond here, proton here, pi bond there. These are isomers of each other. They are actually in equilibrium with each other via this same enolate intermediate. The one on the bottom is called an enol. The one on the top is called a ketone. We'll talk about things that are in their keto forms or keto tautomer versus enol tautomer. It turns out that forming the enol is faster, but the ketone is more stable. So the final product that you get from addition of cuprates to the beta carbon is the ketone. But you make the enol first, and then it equilibrates to the ketone slower over time. Because you make the enol first, and because the two groups that got added are 4 atoms away from each other, we call the enol product a 1,4 addition product. And that name has stuck, and so another way of saying that cuprates attack at the beta carbon is cuprates do 1,4 addition. Another term for 1,4 addition that reflects the fact that the beta carbon is conjugated to the carbonyl carbon via resonance is called conjugate addition. So we're going to use those terms, 1,4 addition and conjugate addition, interchangeably for the rest of the class. The thing that's going to confuse you is if you just draw the ketone product, you're going to be like, how is that a 1,4 addition product? The things that got added are adjacent to each other. They're not 4 atoms apart. And you're exactly right, but the reason it's called 1,4 addition is because you actually do make the enol first. Depending on when you took 351, you probably have seen tautomerization before. You may have seen it before when you did hydroboration oxidation of alkynes, where your first product was an enol, but then it tautomerized to a ketone or an aldehyde. Can't remember which. Anyway, questions? Yeah.
Does it have anything to do with like heat? Because I remember there's like a kinetic thermodynamic.
Does it have to do with heat, kinetic versus thermodynamic? The other time you've heard of 1,2 addition versus 1,4 addition was when you were adding HBr to dienes. And you made a distinction between a 1,2 product and a 1,4 product with thermodynamic versus kinetic. That's not really the same issue here, but you've heard the terminology before, and it's, yeah. What else?
I remember like keto-enol tautomerization happened different in basic versus acidic conditions. Like
Keto-enol tautomerization happening differently under basic versus acidic conditions. Okay, so keep going.
so would we need to know the mechanism of how it tautomerizes into a ketone?
Would you need to know the mechanism for how it tautomerizes to a ketone? At this stage, no, but we're going to do it later. So let me just talk you through it. It's actually, all the details are here. You just aren't seeing them because they're not written for you. To go backwards from the enol to the enolate, what's formed when the oxygen deprotonates water? Hydroxide, right? So to go backwards from the enol to the enolate, what would hydroxide need to do? Just remove that proton, right? That gets you back here. Then you got a resonance stabilized enolate where the negative charge is on the alpha carbon. To get to the ketone, you just protonate on the alpha carbon. So it's 2 simple proton transfer steps. Now that would be under basic conditions. Turns out you can do this under acidic conditions, but we'll maybe wait to do that till never. I don't know if it'll come up. Okay. All right, others. All right, so I encourage you to practice. We don't have a lot of time to practice problems today. I encourage you to do that. What I want to show you lastly is to introduce, and we'll, got 3 minutes for this. We'll do our best. We haven't got a chance of getting to chapter 14 today. I need to introduce the concept of a protecting group for you. Recall that the organometallic reagents are strong bases. So suppose I make this molecule, and I'm hoping that I could add an organolithium reagent, in this case phenyllithium, that's a benzene ring attached to a lithium, and my desired product is this. I want to add the benzene ring, and I want to get now this lovely diol. Instead, I'm going to put the big red X through that, because what happens instead is the proton on the alcohol is a huge problem. The organolithium reagent simply removes the proton from the alcohol. That is a really, really, really expensive way to make a negatively charged alkoxide and benzene. We just made benzene, great. That's like taking several steps back. So, when we have a molecule that's complicated enough that one of the functional groups is problematic, it interferes with the desired reactivity of the carbonyl carbon. Organic chemists have developed a strategy for this. We have to modify the alcohol to somehow turn it into something that lacks an acidic proton. And this strategy is called using a protecting group. The basic principles of a protecting group strategy are: a protecting group needs to be easy to install. By that I mean fast and 100% yield. It must lack the offending functional group, in this case the proton, so that it will not interfere in the desired reaction. And then third, it has to be easy to remove. And again, we mean fast and 100% yield. So the idea here then is that I would do something to the alcohol, a reaction which I would call a protection reaction. PG means protecting group. I could then do the organolithium addition with phenyllithium to get my desired alcohol product. I apologize for the sloppy penmanship. And then in a final step, I will do a deprotection reaction or removal reaction that will unmask or remove the protecting group and get me to my desired product, sidestepping the problematic functional group. Okay? So that's the last topic we need to get to in chapter 13. We will do that at the beginning of next time, and then we'll move on to chapter 14. All right, see you Friday.